In this video, I want to talk about point set topology on complex plane. So basically, when we're talking about real functions, when we talk about domain and range, if you're talking about continuous functions, differentiable functions, you really could just talk about intervals and so on. But because complex numbers are two-dimensional, domain and range could look really weird. So we need a set of terminology to make sense of different types of shapes, different types of properties that these kind of sets have. And that's what I'd like to cover in this video. If you have taken a real analysis course, a lot of these definitions you have seen already. You've either seen the definitions, learned it, and also probably know several different equivalent definitions for these terminology. As far as expectation for this class goes, I'm not going to ask you to prove minor details about these types of terminologies, but it is a 400 level class. You should be able to recite and apply the definitions. So that's the level of understanding that I hope you get out of this video. So here we go. Okay. All right, point set topology on complex plane. So I want to talk about disks. So we're looking at two-dimensional complex plane. So I want to be able to talk about balls, okay? Or in two dimensions, often the word disk is used. So let's see, the notation we're going to use look like this. So if you want to describe a disk, you need two parameters. You need to know the center of the disk, and you need to know the radius of the disk. So that's embedded in this notation. So this is, we use the letter B because in higher dimensions, the word we usually use is ball, but we'll probably use the word disk in this class because we know it's two-dimensional. The subscript here is the radius of this disk. So the distance from the center to the edge of this set. And in parentheses, we're going to list the complex number that will represent the center of this disk. I hope the set builder notation is not new to people, but here's how you read the set builder notation. On the left-hand side, it's the object that could be the member of the set. So most of the time, this is a complex number, which is in the complex number set, colon, and then the condition it must satisfy to be in the set. So let's see, if we have written it this way, the magnitude or the modulus is less than R, that will describe disk centered at the origin because the distance has to be strictly less than R. If you put Z minus Z naught, this kind of shifts the center from the origin to Z naught, right? So this is looking at a disk of radius R centered at Z naught. And that's the quick way to write that condition. Okay. We'll be using that notation a lot. So if you have like a general set, it could be a disk or it could be any other weird looking set. If you have a set S, which is a subset of the complex plane, we say a point on the set is an interior point of the set if you can draw some disk that stays completely within that set, right? And R could be as small as you want. just positive. It can be 0. So if a set looks like this region that I've drawn to the right, and we're looking at that point, we could just pick the radius small enough so the disk is entirely contained in the shaded region. So any point kind of in the middle of the set like that is going to be an interior point. What won't be an interior point is if it's right on the edge, and if the edge is included in the set S, then no matter how small the radius R is, there's going to be some portion of that disk that spills outside of the set S, right? So that would not be an interior point. In fact, there's a terminology for points that look like this. We say a point A, which is a complex number, is on the boundary of S if when you look at a disk around it, there's always a point inside the set and outside of the set. So it touches both inside and outside it, no matter how small that disk is. So there's always a cloud of points that you could dip your hand into, and cloud of points outside that you can stick your arm out of. And actually, this point itself does not have to belong to the set. It could be on the outside of the set as well. Or it could be inside. It could be either, and it could be on the boundary, depending on whether the edge is included in the set or not. Okay, and then the boundary of the set, we're gonna use this notation. So we're gonna use the del symbol, so which looks like a 6 that's mirror reflected, or it's the symbol you use for partial derivatives next to the set. So that means the boundary of the set S. Okay. We say that the set is open if every point in that set is an interior point. Right? So any point in the set, if you pick it, there is a radius that you pick small enough where you stay entirely within that set. That's open. The set is closed if it contains all of its boundary points. So any point that could be considered the boundary is also within that set. That doesn't have to be true, but if it is true if it's a closed set. Now notice open and closed is not defined as an opposite of each other. That it's unfortunate that the terminology kind of it suggests that a set should either be open or closed, but that doesn't have to be true. You could have set that's neither open or closed. You could have a set that's both open and closed. So these relations do not have to be opposite of each other. That's a frequently made mistake. Okay. So let's look at a few examples. So if you have a disk, then no matter how close to the edge you choose the point, you could always pick a radius that's smaller than the distance to the edge so that the disk sits within the bigger disk. So the ball is always open. Notice that this wouldn't be true if it was less than or equal to. If you included the edge will not be interior point. So it's the less than symbol instead of less than or equal to is important here. The entire complex plane is considered to be open, right? So if you're looking at everything, then you can pick any point and pick any radius you like. It's gonna stay within the plane, so it's gonna be open. What's weird is empty set. So if you're looking at a set of nothing, then every point, which is none of them, is an interior point. Vacuously true because there's no point to test. So empty set is also considered open. That might be weird to think about, but it's important to know. These kind of edge cases does pop up. Okay, I kind of mentioned this earlier, but if you had this definition for a disk, except you also include the edge, then it is considered closed, right? So every boundary of the disk is included in that set. So then it is called, considered a closed set. Okay. This might be weird to think about, but if you look at everything in the complex plane, there are no boundaries. Because for it to be a boundary, when you draw a circle, you have to be able to find the points outside of the set. But that doesn't exist if the entire complex plane is the set. So if it contains all of the boundary points, which is nothing, and every set contains empty set, it is considered closed. So complex plane is considered closed. Empty set also doesn't have any boundary. So it's an empty set contains empty set. So it is considered closed. So notice complex plane and empty set are both open and closed. Sometimes these types of sets are called clopen. And as far as subsets of complex plane goes, those two are the only examples like that. Okay, now I want to give an example of something that's neither open nor closed. So sometimes we're going to talk about strips. And this is a half open, half closed strip. So the real part is strictly greater than or equal to 0. And then strictly less than 2. Okay, so in that shaded strip, the real part is greater than or equal to 0 and less than 2. So that's how you get the vertical step. The left edge boundary is included in the set, but it's not closed because the right edge boundary is not included in the set. And it's not open because on the left edge, when you try to draw a disk, it cannot stay within the set. It'll spill out. So it's not an interior point. If you have, I guess, the entire complex plane with a hole at the origin, so everything except for one point, this is considered an open set because no matter where you pick, as long as you choose a radius that stays away from the origin, it's entirely contained in the set, so it's open. It's not closed because that origin is considered a boundary point. It's a weird looking boundary, but it is a boundary. Okay. So it is important to consider closure and the interior of a set as well. So if you start with any set, closure is a set S along with all of its boundary points. So take a union between the original set, so it's bigger than the original set because you're throwing in more points possibly, and you make sure all the boundary is within the set. So that is going to be the closure of the set S. The notation is a little bit unfortunate. We usually describe these by horizontal bar in top of the set. So it looks like it conflicts with the notation for complex conjugate. But that's not what we're doing here. What we're doing is including the boundary. We're not flipping the sign on the imaginary part. So there's no reflection going on. Unfortunately, this is the standard notation. So that's what we mean by that. An interior is sometimes denoted with a small circle on top of that set. So that is, or sometimes int in front of the name of the set S. That means the interior of the set S, which is all the interior points of that set. Okay, so we're looking at possibly smaller set of points than the set S, but these points have a disk around them, so it's interior of a set is going to be an open set. Okay, so very quickly, we want to run through examples to see what closures and interiors look like. Let's see. So the imaginary part of z equals to 2. So this is a horizontal line at the height, the vertical height of 2. So this is already a closed set. The horizontal line's boundary is itself because every disk around that point on the line is going to include that part of the line and also outside of the line as well. You go a little bit above or below and you get set outside of it. So it's on the boundary of itself. So closure is itself. There's no interior point. So the interior of the horizontal line is an empty set. Okay. Let's look at the disk. Okay. So if you look at a disk, the closure will include the circle on the radius. It includes the boundary. So you'll sometimes be called closed disk if you look at a closure of it. The interior of the ball is the ball itself, because it's already an open set. Every point is already an interior point. So the interior of the open set is itself. Okay. Here's an example of the whole plane except origin. So this is a set that we looked at a little bit earlier. The closure would include its boundary. So the closure would just fill in that hole at the origin, and it'll be the entire complex plane. The plane with the hole is already an open set, so interior is going to be the original set. Okay, and then finally, let's see. Okay, the real part is positive, is the right half plane, right? On that side, the real part is positive. The closure would include this boundary, this vertical line, the imaginary axis. The interior would just would not include the boundary. Okay. All right, I want to talk about the idea of connectedness. This is actually much more complicated than how it might first seem. It turns out that it's easier to describe something that's separated than connected. So let's define that first. So we say that non-empty sets X and Y are separated if you can find two open sets U and V that does not intersect, and the open sets contain each part, the X and the V. Okay, so if this is X and if this is Y, sorry, I don't have the stylus pen yet. So U would be an open set and V is an open set that contains Y. So you need like a cloud of points that kind of covers each and that does not intersect. Now, you might think that's a really awkward way to define something that's separated, but you really do need it. Imagine, like, you can't just say, oh, the sets do not intersect and call those separated. But I mean, you could look at, for example, origin, the set that contains just the 1-point origin, and maybe look at an open interval from 0 to 1. Okay. So I'm looking at real numbers here. That point 0 touches the interval from 0 to 1. Although the actual point 0 is not included in the open interval from 0 to 1, because it touches it, even though these two sets do not intersect, you don't want to call this separated, right? So when you try to have an open set around it, no matter what, they're going to have to overlap the U and V that contains the two parts. So if you think about weird cases like this, you'll begin to see why this definition is needed. Okay, so you have a connected set if you cannot separate them, right? So that's how that we cannot have two parts that are separated. Okay, let's look at an example. Let's see. So example of a separated set could be like the entire plane except for the imaginary part being 0. So that's the real axis. So the top and below the real axis is part of the set. These are separated because open set, upper half plane and lower half plane separates these two parts. Okay. An example of a connected set. So this is any complex number where the modulus is greater than or equal to 1. So everything that's not within 1 unit from the origin, I guess. So this set has a hole in it, but you can't separate them into two pieces. Like if you try to cut them, whichever part that you cut is going to have to overlap using the sets U and V. So this is connected. Example connected set. This is example disconnected, or set that's not connected. Okay, all right. So the reason why I have to talk about the connectedness is because of this theorem, which we'll take for granted. I'm not going to prove this because it's actually super difficult to prove, but I hope you could see that it's pretty intuitive. I'm not trying to hide the details here, but that's something that you might prove in topology class. Okay, so most of the time for the domains, we're going to be working with open sets. So we're going to say G is connected if and only if any 2 points in G could be joined with line segments. So what I mean by that is that if you have 2 points, I could draw a pathway just using straight lines that connects them so that these all of the line segments stays within the set the entire time. Now, technically, you might think this is an obvious fact. It's actually not at all obvious. In fact, the reason of the definition of connectedness is separate from the definition of what's called path connected. You could have connected sets that are not path connected. I could maybe show an example. If you look at the graph of sine of 1 over x, it looks like this. It looks like a sine function goes up and down, but because 1 over x kind of blows up when x approaches 0, it starts going up and down so quickly. It'll do that infinitely many times. And then if you include this vertical axis from 0 to 1, this set is connected, but it's not path connected. You cannot draw a path from this side of the graph to that side of the graph because it goes up and down so many times, you cannot draw a continuous line through them because you can't ever get to the vertical line by going up and down. But it's actually a connected set. There's no way to draw an open set that contains the right side and the center line, which separates it from the left side. So they always overlap. So this is a weird set where it is connected, but it's not path connected. This kind of weird example does not occur if you're only considering open sets in complex plane. So because of that reason, which is not easy fact to prove, we're going to be using this theorem. So when we say a connected set, we could assume that we could always connect it with a path. Okay. So yeah, you know all about the subtlety if you've taken the reanalysis sequence. Okay. But the reason why I want to use that theorem is because I don't want to dwell on that subtlety. I want to get to the subject of complex analysis. So I didn't want to distract away from that. I don't want 2 or 3 weeks just to prove that one fact. Okay. One more thing that I want to describe is the notion of a bounded set. So it's bounded if it's contained in some disk of radius r, and r could be super big, right? Like if it's a bounded set, no matter how it looks like, you can draw a big enough circle centered at the origin where it's entirely contained within that disk. Okay, and if you can't do that, then it's called unbounded. So there's points that are further and further away where no radius could contain it. Okay, let's look at some examples. Okay, the first one is any complex number where the argument is between pi over 6 radians and pi over 3 radians. So anything between 60 and 30 degrees. So it's like a slice of an angle that goes off to infinity. This thing is not bounded because you could go very far. It is connected. Okay. Let's see, the second set, okay, the real part, the absolute value of the real part is between 1 and -1. Okay. And imaginary part is between 2 and -2. Sorry, I spilled over to the next page. So I'm looking at a rectangular set like this. This looks to be open, connected, and bounded, right? If you draw a circle big enough, you can contain this rectangle within it. Okay. I'm bringing these examples up because these are type of domains that we will actually use and discuss in the main part of the class. So I want you to be able to look at these conditions and translate it into geometrical shapes. That is something that's going to take practice. And I want you to be able to apply definitions to say if something is open, closed, neither, is it connected, is it bounded? You should be able to answer these. Okay, and practicing that is going to be part of the homework. Okay, one last idea that I want to kind of plant the seed of an idea to you. When we're thinking about real line, there's two different directions for infinities. There's the positive infinity and the negative infinity. And then opposite direction, infinity itself is not a real number, but you know it's a direction, right? You can take the limit towards positive infinity, limit towards negative infinity, and so on. Okay. You might wonder what's happening in the complex plane, because in some sense, infinity is in any direction, right? So are there infinitely many different infinities? Or what do we have here? It's actually more instructive to think about the infinity as one point, which you might think is weird because in real numbers, which is included in the complex plane, we distinguish between positive and negative infinity. But actually, that distinction is not so useful in the complex setting. We could actually think about it as one point at infinity that's very far from the origin. In fact, we'll come to this conclusion in more than one way. But if you can imagine this complex plane as like some kind of made out of cloth, put a basketball at the origin and kind of wrap up the basketball with the cloth. Okay. And I know this is an infinitely long cloth, but kind of if you wrap it up and call the point at the top that you kind of holding with your hand with the excess part of the sheet, we're going to call that point infinity. So in any direction you go, it kind of comes back to that single point. That's how we're going to think about complex numbers. And in fact, later on, I know your calculus teacher has taught you to not consider infinity as a number, but in complex setting, you can kind of treat infinity like any other number. We'll get to that. But yeah, in this setting, it's okay. So if you consider sequences like 1, 2, 3, 4, going to that direction, -1, -2, -3, going that direction, you could also kind of spiral out, right? 1, 2i, -3, -4i, so maybe kind of spiraling out sequence. It is useful to consider this as a sequence that's approaching infinity. If you just look at the modulus, and if the modulus is going to positive infinity, then we say that it's getting closer to infinity in a complex sense. Okay, so this is kind of a shift that I want you to make in your idea of where infinity is. And we'll get the justification of why that's a useful idea later. Okay, I want to end the video here. I'll see you later.